All right, my friends, welcome to section 9.5, arc length in polar coordinates. So we're actually going to be covering arc length and surface area in polar coordinates. Starting with this table, I have this kind of laid out so that really what we're going to do is compare arc length and surface area formulas in all the forms that you will have learned by the end of this section. So rectangular is where we started. Section 9.3, we learned about parametric forms, and then today we're going to transition to the bottom row here, which is polar. So, starting with rectangular form, if you are finding, let's just do arc length in terms of x. So rectangular form for arc length in terms of x would be the integral from a to b of the square root of 1 plus dy dx squared with respect to x. The big square root being there because this was derived from the distance formula. You'll need one in terms of y as well, just in case you're dealing with a function that does not pass the vertical line test, but it passes the horizontal line test. Then you would need to transition and do arc length in terms of y. So the formula there is the integral from a to b of the square root of 1 plus dx dy squared with respect to y. Okay, let's talk about surface area now for rectangular form. So one thing that I want to make sure that everybody knows is that surface area is, in words, we'll write this at the top, is always the same thing. So when you're finding the surface area, you do that by always taking 2 pi, multiplying it by the integral with appropriate bounds, so we'll say from a to b, and then the rest of it is always the radius times the arc length. So if you are revolving a curve about the x-axis, then that would turn into 2 pi times the integral from a to b. And you're revolving a curve around the x-axis, your radius would be your y-coordinate, which we would just say is f of x. And then the appropriate arc length would be in terms of x. There we go. Now, if you're revolving something around the y-axis, and feel free to draw yourself a picture to show yourself that this is true, then your radius would be your x coordinate, and we would call this f of y. So the formula would be 2 pi times the integral from a to b of f of y times the square root of 1 plus dx dy squared dy, sorry. All right, now for parametric form. All right, the good thing about parametric form is you'll only need one. It doesn't matter whether it passes the vertical or the horizontal line test, it's still going to be the same thing. So the parametric form of arc length would be the integral from a to b of the square root of dx dt squared plus dy dt squared with respect to t. Fit it, good job. Okay, now revolving a curve in parametric form around the x-axis, you're still saying 2 pi integral from a to b radius times arc length. It's just, and your radius would be your y-coordinate. You just need to indicate that your y-coordinate would be a function in terms of t. So your surface area would be 2 pi times the integral from a to b, and then we would just say y in terms of t, or y of t, times the square root of dx dt squared plus dy dt squared all with respect to t. There we go. And then revolving it around the y-axis, if you have a curve, you revolve it around the y-axis, your radius would be the x-coordinate. And the way you say that is 2 pi times the integral from a to b of x in terms of t, or x of t. And then times the same arc length formula. All right, my friends, and I hope that feels like review from things that you've learned in the past. The part that will be new is the bottom row where things are in polar, and the most work that we'll have to do is explaining what goes here, and then this will follow very naturally. So, you know what I think would actually help before we start would be, do you mind rewriting this, but just with thetas instead of t's? Okay.
Like right
Maybe right here.
here?
Like, I don't know, even though it's kind of redundant. All right, so Bryce is going to rewrite the parametric arc length form. We're just replacing the t's with thetas.
I'm gonna try and fit it in.
Yeah, thetas are kind of wider than those t's, huh? You got it. Good. Okay. So that's kind of step one to getting a little closer to theta, or sorry, to polar form. Polar form has all r's and thetas as opposed to t or x or y. The next thing that we're going to need to do is basically turn the x's and y's into polar form. And to do this, we're not going to write the integral and everything every time. So what you're going to see Bryce doing is he's going to take the radicand out of this expression. We're going to write it below. And then we're going to show how to change this radicand, just the radicand, into polar form, and then we'll put it back in to the formula when we're all done. Okay, so copying the radicand from the parametric form using a parameter theta. So we're just copying that radicand. So we would have just dx d theta squared plus dy d theta squared. And a note before we continue, to change from rectangular to polar form, x can be swapped out for r times cosine theta, and y can be swapped out for r sine theta. Now just a quick comment for that, if you don't remember that from pre-cal and you haven't watched the section 9.4 videos because I'm not requiring it, totally understandable. Think about if r was 1, you'd be on a unit circle, and this would say x is cosine theta and y is sine theta. But if r isn't 1, it would just scale things up appropriately. All right. All right, my friends. So going from here, the next thing we're going to do is get an expression for dx d theta by taking dd theta on both sides of this expression. When you do so, keep in mind r is a function of theta itself, so you'll need to use product rule for this experience. All right, so we'd have dx d theta would equal, all right, and Bryce and I do product rule in different ways, so I'm just trusting you. There you go. Okay, and dy d theta? There we go. All right. Okay, so now we have expressions for dx d theta and dy d theta. The next thing that we're going to do is square each expression. So we're trying to get an expression for dx d theta squared first. I'm sorry.
That's okay. I think that's
There
good.
you go. Good.
Okay.
Oh, yeah.
Right there.
Told you I wouldn't lose that. There you go. All right, so dx d theta would be the hot mess known as dr d theta squared times cosine squared theta minus 2r sine theta dr d theta cosine theta plus r squared sine squared theta. All right, similarly, dy d theta squared would be dr d theta squared times sine squared theta plus 2r cosine theta dr d theta sine theta plus r squared cosine squared theta. All right, last piece for building up this entire expression that we started with here, we would just need to add our expressions dx d theta squared and dy d theta squared, just adding them together. So in doing so, when you look at the expanded sides of these, the first thing that you might notice is that the messiest, most horrible parts are actually going to vanish because we had like terms and they're exact opposites. And then from there, you'll notice that the dr d theta squared terms are kind of like terms here. And so you could factor out the dr d theta squared, that is. And then same thing for the r squared terms, you could factor out r squared. There we go. And then looky there, you have a Pythagorean identity, and cosine squared plus sine squared is always equal to 1. So this simplifies down, and it's actually super cute. There we go. So if we go back to our table, really all we needed to do was take our parametric form where your parameter is theta and replace this integrand with its equivalent expression in polar form. So if we do this, we would end up with the integral, and I hope it makes sense, we're going to have alpha to beta for our bounds because this is all going to be in terms of theta, of the square root of dr d theta squared plus r squared d theta. There you go. All right, now revolving a graph about theta equals 0. Theta equals 0 is just the x-axis. So if you take any curve and revolve it around the x-axis, your radius would be your y-coordinate, but in polar form, y is equal to r sine theta. So the surface area would be 2 pi times the integral from alpha to beta of y, which is equivalent to r sine theta, times the square root of dr d theta squared plus dx d theta squared, or no, sorry, plus r squared. Wrong thing. D theta. Just let you finish this. All right, if you revolve it around theta equals pi over 2, that's like revolving something around the y-axis. So your radius would be your x-coordinate. So you'd have 2 pi times the integral from alpha to beta, and x in polar form is r cosine theta. There you go. All right, my friends, maybe take a minute and try to memorize that arc length and surface area formula so you can do the last 2 examples. Take care, everybody.